Processing streams. So far in this chapter we have talked about where streams come from: user activity events, sensors, and writes to databases. And we have talked about how streams are transported through direct messaging, via message brokers, and in event logs. What remains is to discuss what you can do with the stream once you have it. Namely, you can process it. Broadly, there are three options. You can take the data in the events and write it to a database, cache, search index, or similar storage system, from where it can then be queried by other clients. As shown in Figure 11-5, this is a good way of keeping a database in sync with changes happening in other parts of the system, especially if the stream consumer is the only client writing to the database. Writing to a storage system is the streaming equivalent of what we discussed in the output of batch workflows on page 411. You can push the events to users in some way, for example by sending email alerts or push notifications, or by streaming the events to a real-time dashboard where they are visualized. In this case, a human is the ultimate consumer of the stream. You can process one or more input streams to produce one or more output streams. Streams may go through a pipeline consisting of several such processing stages before they eventually end up at an output option 1 or. In the rest of this chapter, we will discuss option 3, processing streams to produce other, derived streams. A piece of code that processes streams like this is known as an operator or a job. It is closely related to the Unix processes and MapReduce jobs we discussed in Chapter 10, and the pattern of data flow is similar. A stream processor consumes input streams in a read-only fashion and writes its output to a different location in an append-only fashion. The patterns for partitioning and parallelization in stream processors are also very similar to those in MapReduce and the data flow engines we saw in Chapter 10, so we won't repeat those topics here. Basic mapping operations such as transforming and filtering records also work the same. The one crucial difference to batch jobs is that a stream never ends. This difference has many implications, as discussed at the start of this chapter. Sorting does not make sense with an unbounded dataset, and so sort merge joins, see reduce I joins, and grouping on page 403 cannot be used. Fault tolerance mechanisms must also change. With a batch job that has been running for a few minutes, a failed task can simply be restarted from the beginning, but with a stream job that has been running for several years, restarting from the beginning after a crash may not be a viable option. Uses of stream processing. Stream processing has long been used for monitoring purposes, where an organization wants to be alerted if certain things happen. For example, fraud detection systems need to determine if the usage patterns of a credit card have unexpectedly changed, and block the card if it is likely to have been stolen. Trading systems need to examine price changes in a financial market and execute trades according to specified rules. Manufacturing systems need to monitor the status of machines in a factory and quickly identify the problem if there is a malfunction. Military and intelligence systems need to track the activities of a potential aggressor and raise the alarm if there are signs of an attack. These kinds of applications require quite sophisticated pattern matching and correlations. However, other uses of stream processing have also emerged over time. In this section we will briefly compare and contrast some of these applications. Complex event processing (CEP) is an approach developed in the 1990s for analyzing event streams, especially geared toward the kind of application that requires searching for certain event patterns. Similarly to the way that a regular expression allows you to search for certain patterns of characters in a string, CEP allows you to specify rules to search for certain patterns of events in a stream. CEP systems often use a high-level declarative query language like SQL, or a graphical user interface, to describe the patterns of events that should be detected. These queries are submitted to a processing engine that consumes the input streams and internally maintains a state machine that performs the required matching. When a match is found, the engine emits a complex event, hence the name, with the details of the event pattern that was detected. In these systems, the relationship between queries and data is reversed compared to normal databases. Usually, a database stores data persistently and treats queries as transient. When a query comes in, the database searches for data matching the query, and then forgets about the query when it has finished. CEP engines reverse these roles. Queries are stored long-term, and events from the input streams continuously flow past them in search of a query that matches an event pattern. Implementations of CEP include Asper, IBM InfoSphere Streams, Apama, TIBCO Streambase, and SQL Stream. Distributed stream processors like SAMSA are also gaining SQL support for declarative queries on streams. Another area in which stream processing is used is for analytics on streams. The boundary between CEP and stream analytics is blurry, but as a general rule, analytics tends to be less interested in finding specific event sequences and is more oriented toward aggregations and statistical metrics over a large number of events, for example, measuring the rate of some type of event, how often it occurs per time interval, calculating the rolling average of a value over some time period, comparing current statistics to previous time intervals, for example, to detect trends or to alert on metrics that are unusually high or low compared to the same time last week. Such statistics are usually computed over fixed time intervals. For example, you might want to know the average number of queries per second to a service over the last 5 minutes, and their 99th percentile response time during that period. Averaging over a few minutes smooths out irrelevant fluctuations from 1 second to the next, while still giving you a timely picture of any changes in traffic pattern. The time interval over which you aggregate is known as a window, and we will look into windowing in more detail in Reasoning About Time on page 468. Stream analytics systems sometimes use probabilistic algorithms, such as Bloom filters, which we encountered in performance optimizations on page 4. Set membership, hyperlog for cardinality estimation, and various percentile estimation algorithms. See percentiles in practice on page. Probabilistic algorithms produce approximate results, but have the advantage of requiring significantly less memory in the stream processor than exact algorithms. This use of approximation algorithms sometimes leads people to believe that stream processing systems are always lossy and inexact, but that is wrong. There is nothing inherently approximate about stream processing, and probabilistic algorithms are merely an optimization. Many open-source distributed stream processing frameworks are designed with analytics in mind. For example, Apache Storm, Spark Streaming, Flink, Concorde, Samza, and Kafka Streams. Hosted services include Google Cloud Dataflow and Azure Stream Analytics. We saw in Databases and Streams on page 451 that a stream of changes to a database can be used to keep derived data systems, such as caches, search indexes, and data warehouses, up to date with the source database. We can regard these examples as specific cases of maintaining materialized views. See aggregation, data cubes, and materialized views on page 101, deriving an alternative view onto some datasets so that you can query it efficiently, and updating that view whenever the underlying data changes. Similarly, in event sourcing, application state is maintained by applying a log of events. Here, the application state is also a kind of materialized view. Unlike stream analytics scenarios, it is usually not sufficient to consider only events within some time window. Building the materialized view potentially requires all events over an arbitrary time period, apart from any obsolete events that may be discarded by log compaction. See log compaction on page 456. In effect, you need a window that stretches all the way back to the beginning of time. In principle, any stream processor could be used for materialized view maintenance, although the need to maintain events forever runs counter to the assumptions of some analytics-oriented frameworks that mostly operate on windows of a limited duration. Samza and Kafka Streams support this kind of usage, building upon Kafka's support for log compaction. Besides CEP, which allows searching for patterns consisting of multiple events, there is also sometimes a need to search for individual events based on complex criteria, such as full-text search queries. For example, media monitoring services subscribe to feeds of news articles and broadcasts from media outlets, and search for any news mentioning companies, products, or topics of interest. This is done by formulating a search query in advance, and then continually matching the stream of news items against this query. Similar features exist on some websites. For example, users of real estate websites can ask to be notified when a new property matching their search criteria appears on the market. The percolator feature of Elasticsearch is one option for implementing this kind of stream search. Conventional search engines first index the documents and then run queries over the index. By contrast, searching a stream turns the processing on its head. The queries are stored, and the documents run past the queries, like in CEP. In the simplest case, you can test every document against every query, although this can get slow if you have a large number of queries. To optimize the process, it is possible to index the queries as well as the documents, and thus narrow down the set of queries that may match. In Message Passing Data Flow on page 136, we discussed message passing systems as an alternative to RPCIe as a mechanism for services to communicate, as used, for example, in the Actor model. Although these systems are also based on messages and events, We normally don't think of them as stream processors. Actor frameworks are primarily a mechanism for managing concurrency and distributed execution of communicating modules, whereas stream processing is primarily a data management technique. Communication between actors is often ephemeral and one-to-one, whereas event logs are durable and multi-subscriber. Actors can communicate in arbitrary ways, including cyclic request/response patterns, but stream processors are usually set up in acyclic pipelines, where every stream is the output of one particular job and derived from a well-defined set of input streams. That said, there is some crossover area between RPC-like systems and stream processing. For example, Apache Storm has a feature called distributed RPC, which allows user queries to be farmed out to a set of nodes that also process event streams. These queries are then interleaved with events from the input streams, and results can be aggregated and sent back to the user. See also multi-partition data processing on page 514. It is also possible to process streams using actor frameworks. However, many such frameworks do not guarantee message delivery in the case of crashes, so the processing is not fault-tolerant unless you implement additional retry logic.